Welcome to our lecture on electric flow and electrostatics. So we will discuss here two static equations, one for the electric flow and one for computing the electric field within dielectric materials. We will start with Maxwell's equation in a general form, and we'll discuss the simplifications we can do in order to come up to the electric flow partial differential equation as well as to the electrostatic field partial differential equation. Then we will turn these partial differential equations over to the finite element formulation and we'll discuss clearly in this context the physical boundary conditions, how we incorporate them into the weak formulation and how they show up in the finite element formulation, and what very important post-processing results are of interest after we have solved these partial differential equations with the finite element method. So here is just a summary what you should already know. So these are the full set of Maxwell's equations, which means we have here in this sense the first equation, which is coming up from Ampere's law as shown here. So we have the curl of the magnetic field intensity H given in ampere per meter, and as you know, the curl gives you the vorticity strength of a vector field, and it is equal to the current density. So a current density generates a magnetic field, as we can see here, and in addition, if we have a electric field which depends on time and changes over time, then this is also possible that it will generate a magnetic field, as we can see here. Now, if we stay here within the magnetic field, we want to look here at the last equation. This is equation which has been introduced by Maxwell, and it tells us that the divergence of B is the magnetic flux density is 0, which means the magnetic flux density is a vector field which has no free magnetic charges, or simply speaking, we do not have any magnetic charges, and up to now we have also not found any magnetic charges, which means also, as you know, that the divergence of a vector field gives us the sources in this sense. It is 0. It means it's a pure solenoidal field. Okay, so these are the two main equations we have for the magnetic field. And on the other hand, we have here this equation which tells us that the divergence of D, which is the electric flux density, is equal to QE, the electric charge density. So we have sources and sinks within the electric field, and that is defined by this equation here. It's just the partial differential equation of the integral formulation derived by Gauss. And this is a typical equation defining for us a source sink field, the so-called irrotational field. On the other hand, we have also the possibility to generate an electric field, as you can see here, by a magnetic field if this magnetic field changes over time. And as you know, since the curl of electric field is defined and gives us the vorticity of a field, we see that the electric field can have both parts within a general Helmholtz decomposition, a solenoidal part, which is defined by this equation here, and a irrotational part defined by this equation we have here. Okay, so clearly, as you can look up here, we have two less equations here, and we will need further equations in order to resolve it. Okay, summarizing, based on the empirical laws of Ampere, Faraday and Gauss are Maxwell's equation. Ampere was the first equation. Here, this is the important extension done by Maxwell, important in the sense if we discuss about electromagnetic wave propagation, which will not be the case here. Faraday, the second one, and Gauss, the third one. Yeah, and they can not only describe any magnetostatic or eddy current problems or electrostatic problems, but they can also describe wave propagation. And that is due to the main contribution of Maxwell, the first one, that we have this so-called displacement current density, the time derivative of T, the electric flux density, and the important adding that we have no sources within the magnetic field. It is a pure solenoidal field. Okay, so in this sense, in order to be able to really resolve this set of partial differential equation, we need here these additional constitutive equations as written down here on the slide. So the first one, also sometimes known as the general Ohm's law. So we have the relation between the current density and the electric field via the electric conductivity. And in addition, as you can see, we can also have here induced currents and a current density field when we have a conductive body described by the conductivity being different from zero, which is moving with velocity v in a magnetic field. That can be a static or a dynamic, a time-changing magnetic field, but it can be also static, as we can see here. The second one is the relation between D and E within any dielectric material, could be also active material like piezoelectric material, and it tells us that actually we have the relation between D and E via the permittivity of vacuum, and if we have any materials which you can polarize, then we describe it by additional electric polarization vector. So we also see here that D can have a different direction as E due to the additional polarization. And very similar we have it for the magnetic flux density, that we have the linear relation to H, but if we have a magnetizable material like iron, steel sheets, whatever, then also a magnetic polarization vector comes up. Okay, in general, as already shown here in the combined permeability or permittivity, they can be highly nonlinear, and in a general case, it's even hysteretic. And further on, we can have here the temperature dependency, which is mainly the case for gamma. Gamma heavily depends on the temperature, and that will be also a case we were investigating when we couple the electric flow equation with the thermal heat equation. Yeah, and in a general case, they are not only scalars, as in isotropic materials, the material can be an anisotropic material, and then we have to describe them in such a sense that we use, as shown here, this polarizable, magnetic polarizable, magnetizable vector PM or PE for the electric field, or write here this as a matrix, a 3x3 matrix, also known as a tensor in this sense, because it has some special properties according to the material classes. And we have here then which we can express as a relation between B and H as well as D and E. Okay, Now, if we go on, in our case, we do a stationary static approximation, we should correctly say. So we have no time dependency, as you can see on these slides. So our time derivative of the magnetic flux density as well as also of d, the electric flux displacement, is equal to 0. Which means from the magnetic case we have no eddy currents, we do not consider electromagnetic waves, and this even decouples the electric from the magnetic field, and we get a pure equation for the electric field, the so-called electrostatic field, and then also for the magnetostatic case, which we will not investigate here. Here we will investigate then the electric flow equation. Okay, so as already told, we will come up to electrostatic field partial differential equation, where we have within isolators or the materials no free electric charges. Clearly, we will have at some surfaces electrodes, for example, at which we can apply a voltage or any electric charges. And in addition, we will have the electric flow partial differential equation for the transport of charges through electric conductors. So, as we have the Faraday's law written in differential form as done by Maxwell, and in our case, we neglect here this term because we set it to 0. We have no time dependency. We come up to the fact that the curl of the electric field is equal to 0. Well, and we know when the curl of any physical field is equal to 0, we can rewrite it by the gradient of a scalar function as has been done here. Okay, which also means that due to the fact that the curl of a gradient of a scalar function is always 0, we automatically fulfill this equation here. Okay, and this is expressed here in this sense, this very important property. But what we already can fully summarize is this electric field described by the electric scalar potential will be a irrotational field, so a so-called source sink field, as we know, and can be described by a scalar potential. Now, going back, for example, to Ampere's law and looking for the divergence of this equation here, then we know that this term here is always equal to 0. And on the right hand side, we have the divergence of J plus the divergence of the displacement current density, the time derivative of T, which means when we substitute here the relation that we can express the divergence of T by the free electric charges via the so-called Gauss law, and we also use here the general Ohm's law, which is this here, the relation between the current density and the electric field, via the electric conductivity. We neglect, in this case, any moving bodies now in the magnetic field. Well, then what we will come up, as shown here, is the conservation equation of electric charges as written here, because we know that the divergence of the curl is always 0. And this will give us at the end an electric flow equation which is totally mathematically equivalent to the heat conduction in the static case, as we will see when we also will discuss the thermal heat equation. So now, just in this sense, since we have no time derivatives, we neglect any time derivatives, we immediately get out of this equation here the defining equation for the electric flow field, which, as we can see here, is given by this equation here. So we have the divergence of the conductivity gradient of phi is equal to 0. Again, I want to point your concentration here that we have a derivative of a material parameter, which can even jump by an interface from one material to another material. So that is not as easy to be solved when you directly solve this partial differential equation numerically without going over the weak formulation. Now, it is clear we need the correct boundary condition to come up to a unique solution. And for the boundary conditions, we have here the first one, which is clear. So it is any Dirichlet boundary condition we prescribe here somewhere the electric scalar potential on a so-called Dirichlet boundary, or as we call it, essential boundary within the finite element method. And we can define also a Neumann boundary condition where we can prescribe any current density in normal direction on the surface of this boundary. And this is, as we know, the natural boundary condition, because this will be incorporated into the weak form when we transform the partial differential equation into the weak formulation. Okay, so we have these two boundary conditions where we can prescribe the electric potential or the normal component of the current density. Yeah, and again, this is mathematically equivalent to the stationary static heat conduction. Okay, so what we have is material parameter, as already introduced and discussed, is here the so-called electric conductivity, as we call here gamma. For most cases, this will be a scalar quantity, as also listed here on the slides. A lot of materials of interest we will use for our problems will be isotropic materials, so it is just a scalar. The main dependency already discussed is given by the temperature, so especially when we will have a coupling to the heat equation, then we have to take this dependency into account. And if we not have an isotropic material case, we have a very general material class in this sense, where the conductivity then can be also different in the different directions, then it will be in a general case, hence 3D a 3 by 3 matrix, or also called a rank 2 tensor for anisotropic materials. Okay, so to derive now the governing equation, in this case for the electrostatic field, so the second field we discuss within this lecture here, we again assume that we have stationary fields, static fields. Furthermore, non-conductive materials, for example, we have here no free electric charges, and we assume a linear constitutive relation between D and E via the permittivity epsilon. Okay, from Maxwell's equation we know that we can have the following subset, since we have no time changing magnetic fields. The curl of E is equal to 0, and also the divergence of D is equal to 0. Yeah? We will have, according to boundary conditions on any electrodes, we can prescribe also charges, but for those cases where we will do computations, the electrodes will be so thin that we will not model it as a volumetric structure. So we can incorporate any charges via boundary condition. So these are the describing partial differential equations. Now, as we already know, when the curl of a vector is equal to 0, it makes sense to introduce here a scalar potential, and that is exactly this relation here. Since the divergence of D is always also equal to 0, and we have our constitutive equation between D and E, we come up here to the describing partial differential equation, which is the divergence, our material parameter, in this case the permittivity, most cases a scalar quantity, some cases for anisotropic materials, a 3x3 matrix, or second rank tensor gradient phi. According to the boundary conditions now, which are important to get a unique solution, we can prescribe phi as a fixed value on a subpart of the whole surface of our computational domain. We call it the Dirichlet boundary condition, or within the finite element method, the essential boundary condition. And clearly we can also prescribe surface charges in this sense, which you can see here on a natural boundary of our computational domain, which is the normal derivative. Gradient phi dot n is the normal derivative of phi with respect to n, scaled by epsilon or material parameter. Okay, so in this sense we can prescribe the electric potential or known surface charge densities on the boundary, and also this equation is nothing, is mathematically equivalent to the stationary heat conduction equation. Okay, now we have both partial differential equation for the electric flow and the electrostatic field with the appropriate boundary conditions. Discussing a little bit about the material parameters in an electrostatic computation. Yes, you know, in vacuum we have this simple relation, and perhaps I also want to express that especially epsilon 0 and mu 0, with these two parameters you can compute also the speed of light in vacuum. In a general case, the permittivity can be decomposed for the isotropic cases into a relative permittivity and into the permittivity in vacuum as shown here. Yeah, and if we are also interested in computations where we have anisotropic material behaviors, then this epsilon becomes a rank 2 tensor, which is a 3x3 matrix, and defines the relation between D and E. Clearly not easy. For such cases you need appropriate measurements to get all the entries of this of this rank 2 tensor. Okay, now what we can do is we know our partial differential equations for the electric flow and the electrostatic field. Now let's go over to the finite element formulation, and as you know, our first step is always we introduce a test function and then multiply the test function with the partial differential equation and integrate over the computational domain, as shown here on the slide, our first job, what we do. Then we apply the divergence theorem in this sense that we get here via integration by parts our weak formulation. We can incorporate into the weak formulation the so-called natural, mathematically speaking, Neumann boundary condition. Yeah, and that gives us, as we already trained on this, simply the following formulation, which is shown here. Find the electric potential phi such that we have here to solve this equation where the Neumann boundary condition via the normal component of the current density at the surface gamma n is incorporated and gives the right hand side, and we have as a material parameter here gamma, and importantly, as you know, due to this integration by parts, we have no spatial derivatives operating on the material parameter. So there are no constraints on the material parameter towards also considering problems where we have interfaces of two different materials where gamma is in this sense then jumping. Okay, in addition, clearly the essential boundary condition has to fulfill. Okay, so we have the weak formulation of the electric flow. The same we do for the electrostatic field. Also here we introduce a test function, multiply and integrate over computational domain, apply the divergence theorem, simply speaking integration by parts, and incorporate then the Neumann boundary condition. So in this sense, what we come up here is then the following, that find the electric potential phi such that this equation is fulfilled. Again, here on the right hand side, we see the incorporation of our we see here of any surface charge densities and giving the right hand side. And again here, very important, the material parameter in our case here, this epsilon written as a tensor 3×3 matrix has no spatial derivative. So again here we can consider without any problems then computational domains with jumping material parameters. And the same clearly holds true that also we have to fulfill the Dirichlet boundary conditions being prescribed. Okay, so in this sense we have now our weak formulation, and as we have already discussed in the first lecture and second lecture of this course-defined element method, we introduce then the approximations of the physical quantity phi as well as the test function, and then come up to the system of algebraic equations for the electric scalar potential phi. Yeah, as it is now clear, the primary result here we obtain when we solve the algebraic system of equations, and the primary unknown is the electric scalar potential. The derived results we have within these computations are then in a post-processing results, which will be, for example, the electric field intensity E or current density J. And clearly we also will have integrated results in order how to compute the energy or joules losses in our physical field. Yeah, and so the field results will be then according to any functions of positions, and historical results, for example, we are interested at specific position, what is the electric scalar potential, for example. Okay, so in this sense, that was an overview about the electrostatic and electric flow fields. And we have seen we could derive this simply from Maxwell's equation. Important thing, we consider here just static cases. We have no time dependencies, and we more or less get the same partial differential equation just with interchanging material parameters. For the electric flow equation, it's the electric conductivity, and for the electrostatic field equation, it is the permeability. Yeah, and we can incorporate our important physical boundary condition by prescribing the potential or by prescribing any surface charges or surface current densities. And then when we turn over these partial differential equation to the weak formulation, and according to the finite element method, then by the basis function the approximation of the scalar potential, and obtain algebraic system of equations we have to solve in order to get the electric potential at all our finite element nodes, and can do post-processing to get the Joule's losses, for example, or to get the electrostatic electric field, and so on. Okay,